Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the BSc Physical Sciences students for the paper on applied electronics. And in the last lecture, we saw the photoelectric effect, and in the present lecture, partially we will see as to how the laws of photoelectric emission were explained on the basis of Einstein's photoelectric equation, and hence the contents are Einstein's theory for photoelectric effect and verification of the laws, and mostly on the rest will be on the atom models, starting from the Bohr atom model, SOMMERFELD atom model, and the vector atom model. This is the Einstein's very simple equation for which he won the Nobel Prize, which shows that if a photon with frequency nu is incident on a metal plate, the metal plate requires, or the electron in the metal plate requires a energy h nu naught. H nu is the energy of the incident photon, out of which h nu naught is the so called work function, or the energy required by the electron to come out or escape from the metal. When the electron escapes, the remaining energy, that is h nu minus h nu naught. H nu naught is the energy required to extricate the electron, for the electron to escape from the metal. Therefore, when it escapes, the remaining energy h nu minus h nu naught is the remaining energy that will come as the associated kinetic energy of the electron. That is the Einstein's photoelectric equation. That is something like if you assign 8 electron volt as the energy of the incident photon. As I showed in the last lecture, 2 electron volt is the energy required by the electron to come out in the case of potassium metal. Therefore, out of 8 electron, 2 will go as the work function, or 2 electron volt required for the electron to come out. What the remaining energy? 8 minus 2 is 6 electron volt. This 6 electron volt will come as the kinetic energy of the electron, right? So, the electron will come out with the kinetic energy. Therefore, if h nu becomes larger and larger, the kinetic energy with which it will be coming will be larger. So, supposing if your h nu is equal to h nu naught, what will happen? Half mv square will be 0. If h nu is equal to h nu naught, what is h nu naught? H nu naught is a critical frequency. If h nu is equal to h nu naught, half mv square is 0. That means the electron is just able to come out of the metal. That means h nu minus h nu naught is 0, means h nu is equal to h nu naught. The energy of the incident photon is just sufficient enough to remove the electron from the metal, because nu naught is the critical frequency. These things I have shown in the last lecture. I showed you, if you take a metal plate and if you pass red light to be incident on the metal plate, the electron is not coming out. Why the electron is not coming out? Because the energy associated with red is much lesser compared to the energy associated with the violet ray. You have got the room is illuminated with a lot of light, and all the lights that I am able to see, they constitute the BOHR, violet to red, and you know the wavelength varies from 4000 to 7000. The wavelength of red is 7000, wavelength is large means frequency is less. If the frequency is less means the energy is less, therefore, less energetic photons will not be able to liberate the electrons. Now, these things we saw in the last lecture. There is a critical frequency, there is a critical energy which is required by the electron to come out of the metal. Now, therefore, this is the Einstein's photoelectric equation shown once again. E is equal to hf, that is the frequency, that will be equal to work function plus the associated kinetic energy is F naught or nu naught, as I showed in the last slide. This is the metal work function. Okay, this is the nu naught is the threshold frequency, and as I told you, the contents, the laws of photoelectric emission are explained on the basis of Einstein theory. If a theory were to be accepted, it should be able to explain the facts associated with the experimental observations. And we have seen in the last lecture the laws associated with the photoelectric emission. What are the laws? There is a critical frequency. Secondly, if you have the photon whose energy is greater than critical frequency, the electrons will be coming out. If you keep on increase the frequency, the kinetic energy becomes larger and larger. Secondly, if more number of photons are coming, then the more electrons will be coming. If you have got more number of photons, there will be more number of electrons. Therefore, the photoelectric current is directly proportional to the number of photons, provided the energy of the photons is greater than the critical frequency, right. Therefore, if V is less than V naught, then half mV max square is negative, which is not possible. Therefore, photoelectric emission to take place, nu should be greater than nu naught. That is the nu naught is the critical frequency. Okay. Since one photon emits one electron, the number of photoelectrons emitted per second is directly proportional to the intensity of light. As I told you, if more number of photons are incident, there will be more number of electrons. The photoelectrons, number of photoelectrons which are coming out, it depends upon the number of photons which are incident on the metal plate, or in other words, the intensity of light. The intensity of light is nothing but the number of photons. Then it is clear that half mV max square, that is the kinetic energy associated with the outcoming electron, will proportional to what? Will depend upon the incident frequency. If the incident frequency becomes larger and larger, the associated kinetic energy will become larger. So, the kinetic energy of the electrons is directly proportional to the frequency of the incident light. If the frequency of the incident light becomes larger and larger, the energy associated with the photon will be larger. The work function for a given metal is the same. Therefore, the remaining energy will be coming as the kinetic energy. So, obviously, the remaining energy will be large, and so the kinetic energy will be large. Then lastly, the photoelectric emission is due to the collision between a photon and the electron. You know, a photon is coming and striking the electron. What about the time delay? It is an instantaneous phenomenon. That is, a photoelectric emission is an instantaneous phenomenon. When the light comes and falls, electron comes out immediately. This cannot be explained on the basis of Maxwell's electromagnetic theory. So, the wave theory fails. So, the quantum theory wins. Therefore, as such, there cannot be any significant time lag. There is no time lag between the incident light and the emission of the electrons. So, this phenomenon is an instantaneous phenomenon. It takes place within a time 10 to the power of minus 8 seconds. This particular fact, namely, it is an instantaneous phenomenon which cannot be explained on the basis of the Maxwell's electromagnetic wave theory. So, the wave theory fails. The quantum theory, which was proposed by Max Planck, was successfully applied by Einstein to explain the instantaneous phenomenon that is taking place in the case of the photoelectric. In fact, with this we feel that we are able to explain the loss of photoelectric emission using the famous Einstein's photoelectric equation. Now, we pass on to know about the electrons themselves. We are talking about electrons coming out of metals. What are metals? Metals are composed of atoms. Therefore, a good knowledge about electrons and atoms should be known. Then only the electrons in molecules or electrons in solids or metals can be known. Therefore, the knowledge of electrons, one of the models is the Bohr atom model. All of you know by now the electron was discovered by Sir J.J. Thomson. How do you describe the electrons in atoms? When you want to know about electrons in atoms, what do? You start with the simplest atom, namely the hydrogen atom. That is what was done by J.J. Thomson himself and Niels Bohr. So, Niels Bohr said, let the proton be at the center, the electron revolving in a circular orbit. And when I am talking about circular orbit, all possible orbits are not allowed. It will revolve in an orbit for which the radius will have a particular value. That means the electron is revolving in a shell for which n is equal to 1, that is called a K shell. Then the electron will be revolving in much bigger orbit for which n is equal to 2. So, the electron can revolve or find itself only at certain specific distances from the proton. You got a proton, the electron is revolving in the first shell or the first orbit, that is called a K shell. Then the electron can be found in the L shell. If you give energy, you excite the electron or you excite the atom. The electron is excited means electron is promoted from the K shell to the L shell, provided you are giving energy. And again, if you leave the atom like that, what will happen? The system cannot be in the excited state forever. It is applicable for the human being also. A person cannot be in the excited state all along. So, it has to come down to the ground state. So, from the excited state, the electron should come back to the ground state, that means the lower level. In this process, when the electron is coming from a higher energy level to the lower energy level, there will be emission of a photon. So, you have, when the electron is jumping from higher level to a lower level, I told you n is equal to 2 is called L shell, n is equal to 1 is called the K shell, the K shell, the L shell. When the electron is in the, you can excite the electron from the first orbit, the electron goes to the second orbit, or it can go to the third orbit and so on. The discrete orbits or the discrete energies that the electron will possess is given by the Bohr atom model. What is the success of the Bohr atom model? The Bohr atom model says that the electron in any given atom, say in the hydrogen atom, it will take only discrete energy values. These are the energies. These are the first energy state, the second energy state, the third energy state, n is equal to 4, that is the fourth energy state. The discrete energies that the electron can have in a hydrogen atom is given by the Bohr atom model, that is described in detail. So, for n equal to 1, the energy possessed by electron is 13.6 electron volt as shown here. This is the energy axis. When excited, it goes here, right. Still further, when excited, it goes here. So, when the electron is in the third quantum state, it can come down to the second quantum state. When the electron is jumping from n is equal to 3 to n is equal to 2, what happens? 3 is here, right? 3 to 2. When it is coming from 3 to 2 or 3 to 1, the energy difference will be given out in the case of in the form of a photon. So, light photon is emitted. In this room, I have got light. How do you get light? How do you, or how is it possible for you to get light in this room? You are passing current through the mercury vapor lamp, the mercury atoms, the electrons in mercury atoms are excited and they are coming back de-excited. So, electrons go to higher state, they are coming down. So, this takes place continuously when the excited atom or the electron is coming from higher state to lower state, you get light energy. The photons are coming. Let me have a break at this point. Welcome back at the break. I have been telling you about the Bohr atom model in which the electron in the hydrogen atom can revolve in the first shell for which n is equal to 1, that is a normal case. When you give energy to the electron or to the atom, it will be going to excited state, then it can go to the third shell also if you give much higher energy. And when the electron is jumping from the third quantum state to the second quantum state, when it is jumping third quantum state to second quantum state as shown in the red arrow, similarly red line here, the wavy line is nothing but the light wave that is coming out from the hydrogen atom when the electron is jumping from the higher state to the lower state. When the electron is jumping from the higher level to the lower level, the excess energy possessed by the electron will be coming out in the form of light radiation. That is how you are getting light. You are getting light here because the mercury atoms, the electrons are continuously by giving electric energy, you are exciting the electrons are coming out. That is how light, you are able to get light in this room. Okay. Similarly, in the hydrogen atom, the electrons are continuously jumping from the lower state to the higher state and then to still higher states depending upon the energy that you are giving. And in the reverse process, every system cannot be in the excited state, then they have to come down to the lower state. When they are coming down to the lower state, light is emitted in the form of photons. That is how you get a series of line spectrum, line spectra that you have got here named after Lyman series, BOHR series, Paschen series, bracket series, right. Then you have got Fund series. So, the Lyman series, BOHR series. The most important thing is the whole of atomic physics, the evolution of atom models. Why do you go from, I mentioned in the contents, the Bohr atom model, Sommerfeld atom model, vector atom model and so on, very many models. Why should you have many models? Because you are unable to explain some of the experimental observations. I will now tell you one of the experimental observations which could not be explained by the Bohr atom model, and that led to the Sommerfeld model and vector model and so on. Now, the thing that I mentioned to you now is the following. You look at the BOHR series, right. When the electron is jumping from the second quantum state, that is the K shell, the L shell, the electrons are jumping to the L shell from the higher shells, you know, n is equal to 3, n is equal to 4, n is equal to 5 from these shells, in K shell, L, M, N, O, P, from these shells, when the electrons are jumping down, you get the BOHR series. This line that you have got here, when the electron is jumping from the third quantum state to the second quantum state, this line is of paramount importance. This is of great significance. This is called the H alpha line. Several scientists spent lots of years to explain this particular line. The beauty is this particular single line is called the H alpha line. This line is appearing to be a single line, right? But supposing I am in the Anna University in the College of Engineering Gindi, you put at the top of the clock tower, supposing you have 10 candles, okay. You see from 1 kilometer, what will you observe? Will you be able to observe, see the all 10 candles which are giving light? All the 10 will appear as a single source. You will not be able to distinguish the 10 candles. They will appear as one source. So, similarly here, this line that you have got here is not a single line. It consists of many lines. If you make use of a high resolution spectroscope or a spectrometer, this is not a single line. It consists of more number of lines. I will not tell you how many lines. It is a question which I am posing to you. This is called the fine structure of H alpha line. Now, this made scientists to spend lots of nights and days to explain the fine structure of H alpha line. I should mention lot of scientists who worked day and night or number of years to explain the fine structure of the H alpha line. Is a simple line from the simplest atom that you have got in the whole of periodic table. You know, in nature, the hydrogen atom is the simplest atom. Even this simplest atom, how the electron behaves in the simplest atom, could not be explained for a number of years. So, the beauty of the evolution of atom models, you have to look at the H alpha line. This line is important. This line in the BOHR series, the first line in the BOHR series is very important. This fine structure, the fact that it consists of more number of lines, could not be explained on the basis of Bohr model. That led to the SOMMERFELD model, vector atom model, and quantum mechanics, and so on. Okay. Therefore, without spending a lot of time accepting for the fact that the H alpha line, the fine structure of H alpha line could not be explained, further I should tell you that some of the experimental observations like Zeeman effect, Stark effect. I will not tell you what is Stark effect. You know what is Zeeman effect is a single line gets split up. You take the sodium vapor lamp. You have 58, 90 and 96 angstrom unit. Sodium vapor lamp gives rise to two wavelengths D1, D2. One is 58, 90 angstrom, the other is 58, 96 angstroms. But when you apply a magnetic field, now these lines get split up into number of lines. That is called a Zeeman effect. Similarly, when you apply the same source to an electric field, then again the number of lines gets split up. The single line gets split up into number of lines. The splitting of the spectral lines and the application of magnetic field is called the Zeeman effect. Similarly, the splitting of the spectral line into number of lines by the application of electric field was observed by Stark. The Stark effect, Zeeman effect, the fine structure which I was mentioning just now, these things could not be explained by the Bohr atom model, which led to SOMMERFELD atom model, right. So, SOMMERFELD argued, why should the electron be revolving in a circular orbit alone? He introduced what is called an elliptical orbital theory. For a given n value, you take n equal to 2. For n equal to 2, the electron will be revolving in a circular orbit, then it can also revolve in an elliptical orbit, right. For n equal to 4, there will be 4 orbits. One will be circular, the other 3 will be elliptical. In the Bohr atom model, I showed that n equal to 1, right. What is n? N is called a principal quantum number. Remember, in the Bohr atom model, we had only one quantum number, the so called principal quantum number, which is designated by n. On the other hand, when you go to SOMMERFELD atom model, when n equal to 4, n equal to 4 means there will be 4 orbitals. One will be circular, the other 3 as shown here will be elliptical, and each will be designated by a letter k. K will be there, k equal to 1, k equal to 2, k equal to 3, k equal to 4. There are 4 orbitals. one will be circular, the other 3 will be elliptical. This is called SOMMERFELD atom model, in which case apart from the fact that electron is revolving in circular orbit for a given n value, right, n equal 1 means k shell, the electron in the n equal 4 means what, k, l, m, n. You are talking about the n shell. In the n shell, electron will have 4 orbitals, one of them will be circular, the other 3 will be elliptical. This is the so called SOMMERFELD atom model. This model also had only limited success, right. Let me not go into the details, excepting for the fact, unlike in the Bohr atom model, we had only one quantum number n, the principal quantum number, whereas in the SOMMERFELD model, we have got the quantum number n, the principal quantum number n, and also k. K is called the azimuthal quantum number. The one important thing that I should tell you at this point of time is that you all know about Einstein. Einstein is well known for his theory of relativity, the one man who told about theory of relativity, which led to what? The very important discovery of the atom bomb. So, the atom bomb comes from the special theory of relativity, right, given by Einstein. So, the credit of introducing the relativistic ideas in atomic physics goes to SOMMERFELD. It is called SOMMERFELD's relativistic atom model. He is the first person who made use of Einstein's ideas on theory of relativity and introduced them in atomic physics. So, again I will repeat, the credit goes to SOMMERFELD, because he was the first person to introduce the ideas of relativity laid down by Einstein. He brought those ideas into atomic physics for the first time. The so called SOMMERFELD's relativistic atom model, even though the relativistic ideas were introduced, still the model failed. Let me not go into the details. So, that is the important point, right. The relativistic atom model, it has got 2 quantum numbers, right, n and k. Then we pass on to what is called a vector atom model. Finally, when I complete the vector atom model, you will find that in the vector atom model, there are as many as 7 quantum numbers, right. I will now, in the Bohr atom model, there is only one quantum number n, in the SOMMERFELD model n and k. In the vector atom model, there will be as many as 7 quantum numbers, right. I will come to that in due course of time. The vector atom model is an extension of the Bohr SOMMERFELD model. The 2 important ideas which are introduced in the vector atom model are, one is the space quantization and the other is the introduction of spin of the electron, right. You know, our earth is revolving around sun. All of you know that our earth is revolving, okay. Not only revolving, does it spin? Is it, you know, the earth is revolving. Apart from the rotation, the earth is spinning also, right, the spin motion. Therefore, the 2 Dutch scientists, Uhlenbeck and Goudsmit, I will come to that later, they thought that like the planets which are going around the sun, they are not only revolving, they are also spinning, something like these classical bodies. So, why can't you allow the electron also to spin? That is how the concept of spin came into the picture. I will come to those things later, but what I would like to continue is, as I told you, the Bohr SOMMERFELD model was unable to explain the Zeeman effect, the splitting of the spectral lines and application of an external magnetic field, and similarly the Stark effect. And what is Stark effect? The splitting of the spectral lines, one line appearing as 3 lines or 4 lines. So, the splitting of the spectral lines by the application of the electric field, these things could not be explained on the basis of vector atom model and the basis of the Bohr SOMMERFELD model, which demanded the introduction of the vector atom model. Let me now give the summary of the lecture delivered. It goes as follows. Einstein's photoelectric equation is able to successfully explain all the laws pertaining to the photoelectric effect. Bohr atom model was able to explain the spectral lines. Vector atom model was introduced to explain the other experimental observations which could not be explained by Bohr's atom model. The vector atom model takes into account space quantization and spin. The questions are: explain the laws of photoelectric emission using Einstein's photoelectric equation. Question number 2, briefly describe Bohr-Sommerfeld atom models. With this, we come to the end of this lecture. In the lectures to come, we will continue with the vector atom model in detail. Thank you.